Hello, my name is Cody Kinnear. I'm a fifth-year software engineering PhD student at Carnegie Mellon University, and today I'm going to present my paper titled Building Reusable Repertoires for Stochastic Self-Star Planners, which was co-authored with Bernard van Tonder, David Garland, and Claire Leguez. Increasingly many software systems operate in environments of change and uncertainty. They need to be able to autonomously respond to these changes in order to continue satisfying their quality objectives. Let's dive directly into what will be our running example and case study system for the remainder of the talk, a cloud-based web service provider inspired by Amazon Web Services. The system receives requests from users, which are then routed to a particular region and availability zone, where they're routed to a particular server which can respond to the request. Each availability zone can have its own distinct properties, such as what it costs to provision a server at that location, or the amount of ad revenue generated by responding to a request. An example of uncertainty in the case study is the number of users that are submitting requests at a given time. Since this can't be predicted perfectly a priori, the system needs to be able to automatically respond to increases in the number of requests at runtime. The system can do this with a series of adaptation tactics, like starting up and shutting down server instances at different availability zones, changing the way that the requests are routed between the servers, and also by modifying a dimmer parameter that allows the system to selectively drop some of the ads in order to be able to respond to more requests. Research in self-adaptation has been successful with enabling systems with the ability to adapt. This is often done by adding a control layer over the system that has the ability to monitor the system and its environment, and then effect change by applying adaptation tactics. An important component in these kind of systems is the self-adaptive systems planner. The planner is the component that's actually responsible for determining how the system should adapt. Planning can be done manually, which is often the case in practice, where a human expert will contemplate the different ways that a system might encounter change at runtime, and then specify a series of rules that says if the environment does this, then the system should do that. Planning can also be done in an automated fashion, such as by using probabilistic model checking. Regardless of whether the planning is done in a manual or automated fashion, these approaches often struggle to handle evolution, the changes in the system that occur at runtime that weren't considered during design time, the so-called unknown unknowns. These unexpected changes can come in the form of changes to the available adaptation tactics, such as, for example, it might take longer to start up a server instance at a particular availability zone. There can also be unexpected changes in the system's environment. For example, the web service provider might change their fee schedule for running server instances at a particular availability zone. And also, there might be changes in the quality objective priorities of the system. For example, the company might start to care more about improving user experience and reducing wait times over optimizing the ad revenue generated per user. Whenever these unexpected change scenarios occur, most existing approaches need to generate a new plan entirely from scratch, which, as these self-adaptive systems become larger, more interconnected, and more complex, becomes increasingly expensive from a computational standpoint. One approach that's shown promise in this area is stochastic search, which excels when the search space is large. In our prior work, we presented a self-adaptive systems planner using genetic programming that has the ability to reuse the adaptation knowledge contained in existing adaptation strategies. This planner is able to reuse these adaptation strategies after an unexpected change occurs in order to more effectively replan following an unexpected change. While this approach has shown some promising early results, one limitation is that it could only reuse a single adaptation strategy at a time. An ideal self-adaptive systems planner should be able to reuse an entire repertoire of adaptation strategies in order to have a wider base of planning knowledge to draw upon after an unexpected change occurs. Indeed, many self-adaptive systems already use repertoires of adaptation strategies, often with different strategies designed to handle different contingencies. An example of this is the applicability guards in the Stitch planning language. While the idea of reusing repertoires is promising, it raises several new challenges to plan reuse. For example, how do we choose which adaptation strategies to go into the repertoire, and how do we handle the large overhead associated with reusing an entire collection of adaptation strategies instead of a single one only? In this work, we present an approach for generating reusable repertoires of self-adaptive system strategies for more effective plane reuse. This approach has three main components. First, we use ideas from chaos engineering to explore the change space to generate a diverse set of planning knowledge. We then propose two analysis approaches that aim to mine this base of planning knowledge for planning components that are likely to generalize to future situations and are cost-effective to evaluate. These approaches are clone detection and syntactic transformations. This figure shows the high-level architecture of the proposed approach. In this work, we extend the genetic programming planner from prior work with an offline initialization phase that constructs a reusable repertoire of self-adaptive strategies. This approach can then be further broken down into two parts. In the first part, we use an approach inspired by chaos engineering to build a diverse base of planning knowledge. In the second part, we use ideas from program analysis to mine this base of knowledge to extract generalizable and reusable components. I'll first discuss the approach inspired by chaos engineering, and then I'll move on to the analysis. Chaos engineering is the deliberate application of random failures and perturbations to a system, often done with the idea of robustness testing. One of the most well-known examples of this is Netflix's Simian Army set of tools. One of these tools, called Chaos Monkey, would randomly take down server instances that Netflix used, with the idea of making sure that the system was able to automatically handle these kind of failures whenever they occurred in the wild. Rather than using chaos engineering for the purpose of robustness testing, instead we'll harness the power of chaos to explore the space of changes that could happen to the system and develop a diverse set of planning knowledge to address these various contingencies. To obtain this base of planning knowledge, we use a scenario generator to generate a diverse set of adaptation scenarios that the system can replan for. A scenario consists of 159 different parameters that control the fine details of the system. These parameters control things like how much it costs per unit time to maintain a server running at each availability zone. Also things like the total number of requests coming in and the ad revenue rate. The scenario generator works by randomly mutating one of the parameters of this scenario. More complicated scenarios can be generated by performing multiple mutations to the scenario. After the scenario generator generates a scenario, for example, perhaps it now takes longer to start up server instances at the US East region, this scenario is then given to the genetic programming planner to generate a plan for how the system should reconfigure itself if this scenario were to occur. This process can be repeated multiple times, generating different scenarios and generating plans for these contingencies in order to obtain a diverse set of adaptation strategies that can handle a wide range of different scenarios. Now that I've explained how we use chaos engineering to explore the change space, I'll now discuss the ideas from program analysis that we apply to identify those planning components that are amenable to reuse. The adaptation strategies in our approach are represented in a simple planning language inspired by planning languages like Stitch. This diagram shows the B&F grammar for the planning language. The key takeaway here is that plans consist of adaptation tactics organized by a collection of three operators. The three operators in the planning language are for loops, which allow subplanning components to be repeated for some number of iterations, sequence operators that allow subplans to be chained together, and try-catch operators that allow a subplan to be tried, and then the execution of the plan can change based on whether or not that aspect of the plan succeeded or failed. This slide shows an example adaptation strategy, on the left represented as an abstract syntax tree, and on the right shown in a source code representation. This example strategy consists of a sequence operator that's connecting two for loops together. First, a for loop that's trying to start 5 instances at location C, and then the second for loop is starting 4 instances at location B. The insight here is that because these adaptation strategies are basically simple programs, we can use ideas from program analysis to help us identify reusable components. Here's a motivating example on a more realistically sized adaptation strategy. One of the obstacles to successful reuse is that the genetic programming planner needs to be able to estimate the utility of executing each adaptation strategy on the system. This computation is increasingly expensive the larger the adaptation strategy is, and unfortunately, the most effective adaptation strategies that do a good job of optimizing the system's utility and contain the most planning knowledge often tend to be very large, like this one here. Now, one interesting observation that we made about these adaptation strategies is that more important planning motifs are often repeated multiple times within. One commonly repeated planning component in this plan is highlighted in red. In this case, the plan consists of many nested try-catch operators that are continually trying to start a server instance at location B. So the plan is trying to start the server instance, and then if it fails, it tries again, and if it fails, it tries again, and so on, multiple times. This seems to indicate that it's really important for the system in this scenario that a server instance gets started at location B, as indicated by the plan keeping to test and retry this action. So if we could extract this planning component from the plan, then we could take out the key takeaway from the plan, still have the knowledge that it's important that a server at location B get started, while greatly speeding up the evaluation time by cutting down the overall size of the plan. We present two approaches for this automated extraction of reusable planning components. The first approach uses clone detection, which is a program analysis approach for identifying similar source code regions. While in the program analysis literature, clone detections are often sought to be eliminated as they often indicate technical debt, in our work, we actively seek out clones as indicating generalizable and reusable features. In particular, we use the off-the-shelf Deckard clone detection tool. Our second approach for extracting reusable components is syntactic transformations. Now, one of the advantages of the clone detection approach is that it's easy to apply to any planning language that can be represented as an AST. This makes the clone detection approach very generalizable. However, the trade-off here is that it doesn't take advantage of specific domain knowledge that you might have about the particular domain and the planning language. This syntactic transformation approach allows for the human to manually write syntactic transformation rules that identifies reusable planning components based on their domain knowledge. For example, looking for those nested try-catch operators that we saw in our previous example. In particular, we use the combi tool for writing lightweight syntactic transformation rules. I'll now walk through a simple example for both analysis approaches. Of course, in practice, this will be done with a much larger number of adaptation strategies, and those adaptation strategies will be much larger. In this case, we can analyze this collection of 3 adaptation strategies using the clone detection approach. Here, we identify that there is this commonly repeated start server C motif. This indicates that start server C is likely to be a generalizable planning component, since it occurred in a wide number of adaptation strategies generated for a diverse set of scenarios using our scenario generator. So start server C is an adaptation component that we'll extract. Additionally, we see that this for loop of starting 5 instances of server C is also repeated, and provides another reusable component for extraction. Now let's look at an example using syntactic transformation. Let's write a syntactic transformation rule to extract planning components contained in for loops. This is desirable because the fact that a planning component is repeated multiple times indicates that it's likely important. Additionally, by extracting a component contained in a for loop, we reduce the overall size of the plan, which also makes the plan more cost-effective to evaluate. Here we have an example of a syntactic transformation rule written in combi for extracting planning components contained in for loops. When we run combi on this collection of adaptation strategies, we observe that there are 3 instances of start server C being repeated 5 times, so this provides a planning component that we can extract. Additionally, we also have a start server B tactic contained in a for loop that we can also extract. We investigated 8 different syntactic transformation rules, which we wrote by hand based on our intuition about what might be likely to lead to the most reusable components. 2 of these rules dealt with extracting the contents of sequence operators. 3 rules dealt with extracting the components of try-catch operators. We also write a rule to look for commonly repeated try-catch operators like we saw in our earlier example. We also have 2 rules for extracting components of for loops, both looking at decreasing the number of iterations of for loops by 1, and also by entirely extracting the components of for loops. Now that I've described our approach for generating reusable repertoires of adaptation strategies, I'll now move on to discussing our evaluation. For our evaluation, we investigated how our three-part approach to constructing reusable repertoires compared to the prior work for both plan timeliness and optimality. Our case study system for the evaluation was a simulated cloud web service provider inspired by Amazon Web Services, the same system that's been our running example throughout the talk. We compared several reuse strategies together over 30 different randomly generated change scenarios of varying change sizes. Now, for the purposes of the presentation, I'll be discussing the highlights of the results, and if you're interested in learning more, I'd encourage you to read the paper to see the full results. First, I'll describe the results consisting of using the repertoire on its own without analysis, as well as the clone detection approach compared to the prior work. Since there are 8 different syntactic transformation rules that we investigated, this would clutter up the graph, so I'll discuss these results in the next slide. This graph shows the planning utility on the vertical axis, which is the expected fitness that the system gets by using the planning approach. The horizontal axis is the cumulative evaluation time in seconds, which is how long the planner is spending improving the plan for each of the approaches. The approach with the highest overall fitness was using the repertoire on its own. The next highest utility approach was using the repertoire with the extraction of the clones detected by applying the Deckard tool to the repertoire. Performing below this was reusing a single adaptation strategy only rather than using a repertoire of adaptation strategies. And this is in line with what we did in the SEAMS 2018 paper, so this line represents the prior work. And we also, for having a baseline insanity check, compared to generating a plan from scratch without any reuse, which performed the worst. Now, one interesting takeaway is that the repertoire line doesn't start all the way to the left of the graph, and this is because of the large planning runtime overhead associated with evaluating the utility of the large plans contained in the repertoire. So this approach didn't start returning a plan until after all of the plans can be evaluated, and this is why this line isn't all the way to the left. By contrast, the clone detection approach did start all the way to the left. So this indicates that this approach was successful in reducing the evaluation overhead associated with evaluating these adaptation strategies. So in a planning domain where timeliness is very important, like a fighter aircraft or a self-driving car, then using the Deckard approach might be superior to using the repertoire on its own, since these resulted in improved fitness compared to planning from scratch or planning with a single plan only. However, this approach was still delivering plans just as fast as these approaches. On the other hand, in a planning domain where timeliness is less important, so for example, say a Roomba robot trying to generate a new path while it's charging, if you're willing to wait longer for an adaptation strategy to be available, in this case it took around 12 to 13 seconds to generate the first plan, then waiting for the repertoire might be best, since this approach took longer to get a plan, but once the plan was returned, the approach obtained the highest overall utility. I'll now discuss the results investigating the 8 different syntactic transformation rules that we investigated. Rather than showing a single representative execution, as we did in the previous slide, this slide's table shows the overall aggregate percent improvement for each of the 8 different syntactic transform rules. This percent improvement is relative to using the repertoire on its own, since as we shown previously, this approach resulted in the overall best of the other approaches. There were 4 different syntactic transformation rules that resulted in an overall improvement. Those transform rules were extracting the first component out of the try-catch expression, extracting the third component of the try-catch. Additionally, removing components contained within for loops performed well, and also the rule that extracted components in repeated nested try-catch operations resulted in a positive improvement. The approach that resulted in the best improvement by far was the try-take-first syntactic transformation rule, which extracts the first component of a try-catch operator, which is the component that is being tested. This makes sense intuitively, since if we care about whether or not a particular subplan is succeeding or not, then likely that component is important. This particular transform rule resulted in a consistent improvement, improving 29 out of the 30 scenarios that we investigated.
and it resulted in a 3.5% overall improvement, which is an additional 3.5% improvement over using just the repertoire on its own. Before concluding the talk, I'll discuss some of the high-level takeaways from the results. Using the repertoire approach on its own, consisting of only the chaos engineering aspect without any of the analysis, resulted in an overall aggregate 11% improvement over the prior work. Using the clone detection approach on top of using the repertoire on its own resulted in more timely planning, however, the planning utility wasn't as good as using the repertoire on its own. The overall best approach was using the try-take-first syntactic transformation rule, which resulted in a 15% overall improvement, and was also just as timely as using the clone detection approach. In conclusion, building reusable repertoires of self-adaptive system strategies can help these systems to replan more effectively following an unexpected change. In this talk, I presented our approach combining ideas from chaos engineering and program analysis, consisting of both using clone detection and syntactic transformation rules to create reusable repertoires of adaptation strategies that are both likely to generalize to future situations and are also cost-effective to evaluate. Overall, our best approach showed an improvement of 15% over the prior work. Thank you.